All right, so now we've played the main game, sampling distribution of means, and it's time for the DLC, sampling distribution of proportions. That's a gaming reference. If you don't know it, don't worry about it. October's wide awake and ready to learn. Actually, she's distracted, so don't use her as an example. Let's talk about sampling distributions of proportions. So when we look at a sample, we can have a sample mean if we have numerical data. Average weight of watermelons, average height of people, average number of televisions that somebody has, whatever. Well, if we look at categorical data, now the parameter of interest is a proportion. What proportion of flowers are purple? What proportion of people support a recycling law? Okay, for categorical data. What proportion of people rated their patients? What proportion of patients rated their pain of at least 4? Okay, that'd be ordinal categorical data, okay? So we're going to start with another example. Forget the watermelons for now. Now we're rolling a fair die 60 times. All right? Or you can think of it as rolling 60 dice once. That's more fun, I think. Let's roll 60 dice once, fit them all in your hands and roll them around. And we want to find what proportion of ones should show up. What do you think is going to be the answer, right? What would you expect? You would expect about 1/6 of the dice to show up as ones, right? But it's going to be different. Every time we roll these dice, sometimes we'll get like 1/6 of them would be 10 dice being one. So sometimes we'll get 10 dice, sometimes 12 dice, sometimes only 8 will be ones. Maybe we'll get really lucky and get 20 dice that show up as ones. But every time we roll it, it's going to be random. That's what sampling distributions are all about. Every time you take a sample, the mean that you get from that sample or the proportion that you get from that sample will be a different number. The distribution is, okay, well, how are those different numbers random? Where do we expect those numbers to be? And again, in this case, right, we'd expect that every time we roll them will be different, but we'd expect on average 10 dice to be ones. On average, we'd expect a proportion of 1/6. How spread out would those be? That's more complicated. So we're going to visualize it with a similar website. Okay, so let's roll some fake dice. So here's how this website works. I'm going to roll 60 dice one time. All right, I rolled 60 dice. 7 of them were ones out of our sample size of 60. What proportion were ones? About 12%, about 11.7% were ones. We are going to now use a dot plot to track that information. Let's roll 60 dice again. Again, we'll probably get something different. We'd expect about this many. Let's roll 60 dice again. All right, now we got 9 of them that were ones. That's a proportion of about 0.15. Put it on the dot plot. Roll again. Oh, we got 13 that time. That's a proportion of 0.216. Now we can keep on rolling 60 dice, keep on rolling 60 dice, keep on rolling 60 dice. If we do this a lot, what shape do you think we're going to get? As we roll 60 dice, we have this nice dot plot. What shape do you think is forming? Let's do 100 at a time. Interesting. This should look a little familiar. 1,000 at a time is a little slow. Now we got something a little different. This is actually a discrete distribution. It's not continuous, right? Maybe we got 10 dice showing up as ones. That'd be this proportion. Or maybe we got 11 dice showing up as ones. That'd be this proportion. But it's actually impossible to get a proportion between these two because we're either going to have 10 dice or 11 dice, nothing in between. So this will actually be a discrete distribution, but we can still model it with a normal distribution. Okay? And that'll still be useful. All right? So this is what sampling distributions for proportions look like. And again, we have something normal. So let's write some notes about what we're seeing. As we do this, the original population is over here. What is the population proportion? Well, the original population, that's going to be the proportion of dice we expect to be ones. And again, this proportion is a 1/6 for us. And specifically, of single dice. Sorry. No, I think it makes more sense to say proportion of all dice. All dice for the population. The proportion of all dice we would expect to be ones would be a 1/6. And then we took a sample. This shows how many were 6 in one sample of 60 and what proportion they were. Okay, how many were ones out of the 60 we looked at? And then also what proportion is that? The distribution of proportions, that was this window, right? That was a dot plot. A dot plot of all our samples. I can't write the word samples. So again, this is very similar to what we had before with means, right? With means, we had a population, we had a sample, and then we had the distribution of those samples. Very, very similar, just looks a little different. We have a dot plot now. Okay, so some more questions if I can find them. Looking at the statistics on the upper right of the window, what does the mean represent? What does this mean represent? Well, it's for the dot plot. It's out of all of the rolls we've done. And we've rolled 60 dice 8,500 times. Out of all of those rolls, what proportion did we average? About a 6. That's a 6 as a decimal. Okay, so that mean is the average proportion from our, what was it, 8,501 rolls of 60 dice. And again, sometimes, look, there was one time where we only got 3% of them as ones. There was one time where we got almost 1/3 of them to be ones. On average, 1/6 of them were. Describe the shape of the dot plot. Looks kind of like a normal distribution. It's not perfect. In fact, it's a little skewed here, a little skewed to the right, but it's roughly normal. It's a little skewed. What if we only look at 10 dice? All right. If we look at 10 dice and we do the same thing, what happens? Oh yeah, 10 dice. I don't care how many samples we do. 10 dice is not going to look normal at all. There's much bigger gaps for starters, smaller sample size, there's fewer options. And yeah, it's going to be totally skewed to the right. That's not normal at all. So it's not normal. This is if n equals 10. It's not normal. We have big gaps. It's skewed right. And let's change this to 500 dice. Make this a little bit more interesting. If we do 500 dice, what do you think is going to happen? Normal or not normal? Let's see. 100 at a time. Oh yeah, 500 dice is looking good. And again, the more samples we take, the more normal it's going to be. You need to take a lot of samples to get it really normal. And again, it's kind of fuzzy still, but that's just because of the sample size. Also, it's just, these all are the same distance away from each other. It looks like these two are closer and these two are further. They're the same distance. It's just the computer that's drawing them like this way, just limits of the technology. Yeah, it's roughly normal. Okay. Again, it's roughly normal. And we have small gaps. And then one more thing I didn't comment on is even if the sample size was 10, look at our sample mean. Even with a small sample size, even if it's not normal, we still expect on average for about 1/6 of the dice. I froze it. I clicked too fast. The computer is really, really stressed out now. But yeah, we'd still expect, there we go, about 1/6. Which is interesting because 1/6 is never possible with 10 dice. Right? You can either get 2 or 1. You'll never get 1.6 dice out of 10, but it's still the average. All right. Great. What happens to the sample proportion as the sample gets large, sample size gets larger? And what happens to the standard deviation? Again, this is similar to the population. And as the sample size gets larger, sample standard deviation gets smaller. Just like we had with means. Doing 10 dice, the standard error is about, which is the standard deviation. The standard deviation is about 0.117. If we look at 500 dice, that's much smaller than 0.117. In fact, like about 1/10 as big. All right, so that's the introduction here. We've got something really, really similar. We'll talk about it in the next video, but what our sampling distribution looks like for proportions will be very similar to what our sampling distribution looked like for means. Just a little different. Stay tuned. That was our intro for this one.